Hi everybody. Today we're going to be covering section 15.8, which is called Lagrange multipliers. I think that's the last thing in chapter 15. It is. So then we'll be coming up to chapter 16 soon. So I wanted to show you sort of a motivating example of the concepts behind Lagrange multipliers. And to do that, I've made an imaginary contour map of some region. You can tell there's 3 mountains here. Can you tell which mountain is the tallest? This guy. See how many rings there are around the peak? There's several more changes of elevation. You're going, let's see, from about here, we're on the same, somewhere in between these two, we're at the same level. There's sort of a route to all 3 peaks. Well, here. Oh, I don't know. Anyway, I'd have to cross through many more lines to get through to this peak than I would to get to that peak. And I think this is the tallest, that's the next tallest, and that's a relatively small one. So it doesn't matter that much. The idea of Lagrange multipliers is to think about a path that is in the xy plane. And of course, these contour lines represent something where z is a function of x and y above that plane. But you've got a path that lies down in the xy plane that runs through some territory like this. And you want to ask yourself, where along this route are we at the highest elevation? Or similarly, where are we at the lowest elevation? Now, that's relatively obvious, I think, on this one. Right here, I'm going uphill, but then I'm going back downhill, returning to the same level. Here, I guess I'm increasing a bit to get to that elevation, and then increasing some more to get to that elevation, increasing yet more to get to this next line, and then decreasing. So does it make sense that somewhere in there is where we're at the highest as we traverse this little route? Well, what's interesting about that location, if you notice it, the path, I guess I was thinking about moving this direction. So the path through that point is parallel, in fact it's tangent, to the contour line at that point. I'm darkening in the contour line so you see it. So when we're at the highest spot, we're running parallel to a contour line. That actually makes great sense if you think about it. If you were crossing the contour line, you're still either going up or down. But when you run parallel to it, you've kind of reached a max. Now, on a map like this, well, let me change gears a second. How do you locate when you've got one of these cases where the path is going in the same direction as the contour lines are? It's actually interesting that you sort of concentrate on 90 degrees to that. You see, the contour lines have vectors, gradient vectors, that are perpendicular to them. So the gradient vector for your function will be perpendicular to that. The line that we're following, the path that we're following, may not have such a gradient vector ordinarily. But there's a certain situation in which you can say it does. So what if this line, this red line, was actually defined implicitly by some function equaling to a constant? That means if that's g of xy equals k, there's probably another line parallel to it. In fact, there is. We could define it, which would be defined by g of xy is k plus 1. Now, what direction does the gradient follow? It goes from a spot on the k level in the direction of the k plus 1 level. So the gradient of that g, I guess I can stick with red here, goes this way. And what do you notice about grad f and grad g? Well, in this case, they point in opposite directions. If the k plus 1 level had been on this side of it, they'd be pointing in the same directions. The real issue is that whether they're pointing in the same direction or not is just a question of whether they are, well, they're multiples of one another, but is that multiplier a negative or positive? The main deal is that they are parallel. And that leads to what's known as the Lagrange condition, which I'm going to write down for you in a sec. Well, yeah, let's write it down now. I just need to make a little clear area to write. The gradient of the function f is some multiplier times the gradient of the function g. Those are two gradient factors. That symbol is the Greek letter lambda. Lambda. And it's used in physics for wavelength, I believe. Or is it frequency? No, nu is frequency. Anyway, it's a pretty common Greek letter. And the person who invented this whole method, his name was Lagrange, so I think the L is supposed to be sort of an honorific for Lagrange. Okay, so that's how the method works, basically. We're going to locate places where the gradient of the function and the gradient of, well, another function, but really we're looking at the g equals to a constant curve where they're parallel. It's interesting that we care about them being parallel. I don't really give a crap about what lambda is. I just want to know that there is such a lambda, that the gradients line up. If you look somewhere else on this graph, for instance, right here, the gradient of the black stuff is going that way. The gradient of the red stuff is going that way. These are not parallel vectors. All right, so that's sort of getting started on the method. We'll do a couple of examples which will set it straight, but before going too much further with it, let's talk about why we would be doing this method. In Calc 1, you had situations like this, where that's supposed to be an x-axis. You might have a function like that, defined over an interval, say from A to B. Okay? And you're interested in the maximum and minimum values of this function. That's meant to be a closed interval. So if you want to find the max and or min values, I tried to spell values with an F here. Values of f of x on the interval AB, you had to do two things. You had to, one, find the derivative and solve where the derivative is equal to 0. That gets you critical points, and then you work with the critical points to locate which one is the highest. And the other thing is you have to check the boundary. Check boundary of the region. That is, in this case, the value where x is equal to a and to b. So let me just do this graphically. There is a critical point, a place where the tangent is horizontal. Here's another critical point. Checking the boundary gets me down to here and up to there. Now, if you look at these four locations, this is clearly the minimum. In fact, that's known as an absolute minimum. I think that location is the maximum. We've got a minimum there, but it's merely a relative minimum. And this one is nothing. Null set. It's neither a max nor a min, but it's just a place we should have checked. Because look at the other endpoint, we did get one of the extreme values. Well, conceptually, what we're going to do in the multivariable setting is kind of the same. So here's the idea. You're going to have a function. So we're going to find extreme values again for a function of two variables. on some particular region in the plane. So you may visualize the function as contour lines. And then the region, I wish I could make a more interesting set of contours, but let's do a region that is like, a big circle. Trying to make that as circular as possible. I don't think I'm doing that great of a job of it. I'm going over it a few times to make it look big and red. So this is our region R, and the black stuff, the contours, is our function. Now, the max value you can spot here. It's at a place where the gradient of this black stuff disappears. So it's the peak of that mountain. So that's your maximum value. But where does your minimum value occur? Well, I think that occurs on the boundary. Now this boundary, I mean, do you get the similarity to the previous question we had? This boundary has places where the function is maximum and where it's minimum. And those happen when the gradient vector for f, and thinking of r's boundary there as a function, there could be, if that's a circle, it might be x squared plus y squared equals a constant. So there'd be a whole bunch of concentric circles that went with r. Anyway, r has a gradient vector too. Those two are parallel right there. There's another spot where the boundary of the region's gradient and the function's gradient are parallel. It'll be right in here. Yeah. So we'll take the gradient, which is like the first derivative, and we'll set it equal to 0, and we'll locate critical points like that one where we find the max. But we'll also use the method of Lagrange multipliers on the bounding curve and find places where, constrained to lie on the boundary, you'll either be at a max or at a min. And places where the gradients are not in the same direction, you're either going downhill or uphill. Oh, actually, it looks like right in there's another one where, whoops, wrong direction. That gradient and this gradient are both the same. Interesting. That's the lower of the two. That's a slightly higher thing, but here we're going downhill the whole way till we get to a minimum. So there must be another one too. It turns out there's always an even number of these around a closed curve. Well, in this situation I've got now. Yeah, I can see it right there, and there. We've got parallelism of the gradient vectors. Okay, so we'll sort of work on the interior of the region in a thing that's quite analogous to Calc 1. Take the derivative, set it equal to 0, solve for critical points. If you like, we can even do second derivative tests on those kind of points to see whether they're maxes or mins. But in addition to that, we'll be looking around the boundary of the region. My boundary here is just a circle, which would be great, really easy, but often boundaries are more complicated. Sometimes we have to break the boundary up into a bunch of curves. Like, if you're looking at the boundaries of some state, like US state, right, then often they're north, south, east, west lines in a lot of states. Connecticut's kind of like that with a few bumps on it. All right, so let's push on and do an actual example of this. Sorry, before we actually do an example, I needed to kind of give you a way to conceptualize the setup we're dealing with and to really get some terminology in. So this technique we're learning, the method of Lagrange multipliers, is an example of what's called constrained optimization. There's a constraining condition, basically that we're laying on some path in the xy plane. Optimization is the generic way to refer to finding best values. They sometimes are best when they're at a maximum, sometimes best when at a minimum. So we'll just say we'll find them all. We'll find both maximum and minimum values of some function. So the function will be a function of two variables, and it'll be subject to a constraint. And this is how we'll say the constraint. The the constraint is implicitly defined as the k level curve of some function g of xy. There's some additional terminology I want you to know. The function f of xy is called the objective function. Or simply the objective. I'm going to write func. Objective func. G of xy equals k is the constraint. Well, those are the two main ingredients. Wow, I said g of xy equals k, and then here I didn't write it. One of the things is equal to a constant. That's the constraining condition. And the other is just free. It doesn't have a set equal to k. That's the one that you're trying to find the max or min value of. Well, let me say in general how we're going to proceed, and then we'll actually do it. So just keep this in mind. We're going to use f as the name of the thing we're trying to maximize, and g of xy is going to be, well, one of the level curves of g of xy is going to be the constraining condition. We lie on that level curve, but we're trying to find the max and min of this one. So what's the technique? You're going to calculate both gradients, find grad f and grad g, and set up a system of equations. One of them looks like this, that grad f is equal to lambda times grad g. Well, I say one of them. That's actually a whole bunch of functions. The other one is going to be that you lie on the constraining condition, so that g is equal to a constant. So typically this guy is two equations, and this one is a single one. I don't know what you're going to do to solve that, but you're going to have to. So that's our setup. Grad f times lambda times grad g, and then also the constraint has got to be true. All right, so with that terminology in hand, here's a typical optimization problem with constraints. You're going to optimize the function. I've just got a nice simple one, x times y, subject to the constraint x squared plus y squared equals 1. So our objective function is the product x, y, and our constraint condition is that the sum of the squares equals 1. All right, so how do we do it? Well, first figure out what grad f is. These are functions of two variables, so the gradient vectors will just have two components. When we take the x partial of this expression, we get y. And when we take the y partial of it, we get x. Right, so grad f is yx. The g here is x squared plus y squared. I'll just say that first. It's the stuff on the left-hand side, and then what it's set equal to is the constraining condition. So grad g is equal to 2x, comma, 2y. Now there's an interesting shortcut you can do when you're doing Lagrange stuff, which is if there's a constant, like there's a 2 in both of these, you can just ignore it. You can just pull it out and ignore it. It's sort of, in a sense, included with the lambda, because you only care about the direction of these vectors, not their particular length or anything. In any case, let's set up the system of equations we're supposed to deal with. To say that grad f is a multiple of grad g, that is, looks like this, grad f is equal to lambda times grad g. By the way, I don't think I mentioned it, but people technically call that thing the Lagrange condition. And the other thing we're going to see is that g is equal to 1. Let's see. Yeah, no, I'm just going to say g because we know that's a function of x and y. Well, that's sort of saying what the things are generically. Let's do it in our example. What does this vector equals lambda times this other vector really mean? And what does g equals 1 really mean? So the Lagrange condition becomes y comma x is equal to lambda times 2x 2y. And the constraining condition is x squared plus y squared equals 1. Now that top thing, is it being a vector equation, is actually two scalar equations. So let's write them down separately. What's going on in the x coordinates and what's going on in the y coordinates. The x coordinate says that y is equal to lambda times 2x. The y coordinate says that x is equal to lambda times 2y. And then the constraint condition is that x squared plus y squared equals 1. Well, what do we make of all this? There's multiple ways to proceed, but one of them, which is fairly common, because these are nonlinear equations. They're, well, actually the first two are, but that part's certainly nonlinear. Anyway, there's no generic way to say here's what you do, but there's often similar tricks that work. And one of the things is we want lambda to exist, but we really don't care what it is. We don't care what the value of lambda is, meaning if you got to eliminate a variable, eliminating lambda is pretty reasonable. So if you solve both of these for lambda, this first one will become lambda is equal to y over 2x. The second one is going to become lambda is equal to x over 2y. Just divide both sides by 2y, or in this case 2x, right? And here's what I mean by eliminating them. If that expression is equal to lambda and this expression is equal to lambda, well then these two guys are equal to each other. So we'll have one fewer variable now, but we've also got one fewer equation. We've got that y over 2x is equal to x over 2y. And then the other equation is just the constraining condition, x squared plus y squared equals 1. Well, I'm not done. If these two fractions are equal, then I know that x is non-zero and I know that y is non-zero because you're not allowed to divide by 0. So you can multiply both sides by 2x. You can multiply both sides by 2y as well, or what some people refer to as cross multiplication. So when you write this thing one more time, it says 2y squared is equal to 2x squared. And the sum of x squared and y squared is 1. Does it make sense that we can just knock off these 2's on both sides? Y squared is x squared. Great. There's a lot of steps in this algebra which I'm doing them in sort of full detail for you right now, but later we would be able to move a little quicker with this once we've got some experience with it. Anyway, substituting y squared is equal to x squared into this, we get that x squared plus x squared is equal to 1. Or 2x squared is equal to 1. Or x squared is equal to 1/2. Or finally, x is plus or minus, should I say root 2 over 2? I'm just going to say square root of 1/2. All right. Then what's y? Well, y squared is the same thing as x squared. I know what x squared is, it's a half. So we also have y squared is equal to 1/2 as well. So y is also going to be plus or minus square root of 1/2. Let's try to visualize this. What we've got here is two different conditions. One is that x is plus or minus root 1/2. The other is that y is plus or minus root 1/2. That actually turns into 4 locations in the plane whose coordinates are equal to plus or minus square root of 1/2. A little bit off, isn't it? So like this would be 1 over root 2, comma 1 over root 2. This would be the same except with a minus sign on the y coordinate. This has them both negative. And let's see, this is the x is negative, the y is positive. Oops, positive 1 over. Those are the 4 points. Now, I think a sketch might help us a little bit. So let me give you a crude idea of what this looks like. First off, what do the contours of f look like? Well, f of xy, remember, was just the product. So what does, for instance, x times y equal 1 look like? Solve it for y, and it looks like y equals 1 over x. That's a very well-known looking graph. Looks like that. So that's the one level curve for our function. If x and y were both negative, we'd also get this piece of it. So that's also level 1. Level 0 turns out to be the 2 axes. If the y-axis is where x is 0, so you'll get 0 as the output. The x-axis is where y is 0. So level 2 would be like in here somewhere. Or in, shoot, here somewhere. Negative levels would be like that. And that. Not sure where to write the level on that one. -1 here. -2 farther out. You get the idea now. You can see from the contours that there's a saddle point right here. If we leave the origin, which is at height 0, heading this way, we'll go down towards negative values. If we head in the other direction, we'll go towards positive values. My constraining condition is that we're on the curve g of xy equals 1. That should pass. Oh no, it doesn't. It passes. It looks about like this. That's what x squared plus y squared equals 1 looks like. And the 4 points that I located over there are here. And here, there are these spots. You might recognize this from trig as the cosine and the sine of 45 degrees. Right, so those are our locations. The constraining function, well, the constraint condition is that x squared plus y squared equals 1. Let's look at some of the other levels for that. X squared plus y squared equals 0 is there. It's just a point at the origin. X squared plus y squared equals 2. I think that's the one that's going to be tangent to those level curves of height 1. Bad. Do you see that this place, and let's try to put in a level curve that goes through at position, sort of, I don't know what level this would be, but, well, it'd be level 1 over root 2, I think, anyway. Certainly parallel to those, or roughly parallel to these other guys. And you see that there's the black curve's gradient, and the red function's gradient is in the same direction there. But that also happens here, and here, and here. Well, that was kind of fun. We found, oh, well, one thing I didn't do is tell you which are the maxes and which are the mins. Maybe from the picture it's obvious. When both coordinates are positive and when both coordinates are negative, you're at the high spots. When both coordinates are mixed, one's positive and one's negative, then you're at the low spots. So if I get this bright idea that I might help you try to visualize what the shape, the height of the thing looks like as we go around this circle. So seen from above, that's crudely circular, but the idea is that we'll rise up on the front part of the saddle, descend along where the legs would go, and then as we come back this way, on the back edge of the saddle, there's a high spot, and then there's another low spot. Those happen along the line y equals x and y equals negative x. Yeah, that's probably hard to see in the, anyway, some kind of an indication of it in 3 space. All right, here's another example to try out. The difference here is that I've phrased it more as a word problem, so it's maybe not clear what the objective function is and what the constraint is. That's an issue. But a bigger issue is that it's 3-dimensional. Right? I've got a plane in 3 space defined by that equation. So clearly we're looking for a function that's a function of 3 variables. All right, so it turns out the Lagrange condition in 3 variables just creates 3 scalar equations, whereas a minute ago it was 2. And you can still do this. You can still do the whole Lagrange setup. So our big deal is to figure out what are the function we're trying to optimize, and oh shit, I just pointed at it. And what is the constraint? G of x, y, and z equals to some constant. What are these 2 pieces? Well, it's in the words. We're looking for the thing closest to the origin. So the function should be our distance from the origin. Square root of x squared plus y squared plus z squared. That is your distance from the origin. A nice simplifying fact, and one that I find I use all the time, is that if the actual distance is minimized, then so is the square of the distance. The squaring function on positive numbers, and distances are positive, is monotonic, so there's no reversal of inequalities or anything. So what does that mean? In the final analysis, it means I don't need that square root. Oops, drop something. That is, I can optimize the square of the distance, and it'll do the same thing as optimizing the distance itself. What about the constraint? Well, you're looking at it. It's in this thing. We're going to lie on this plane. So we're looking for a point that lies on that plane, which is closest to the origin. So g of x, y, z will literally be x plus 2y minus z, and k would be the 5. It's typical that if you've got something that looks like a formula equals a number, that'll be the constraining condition. All right, so I don't know if I should have said equals. F of x, y, z is that. G of x, y, z equals k becomes x plus 2y minus z equals 5. Cool. What's the Lagrange condition? That grad f is a multiple of grad g? Well, grad f isn't so bad. That's 2x, 2y, 2z. And grad g is really easy because this is linear, so the gradient is got constants in it. 1, 2, and -1. I made a comment before that when you're doing these Lagrange things, all you care about is the directions of the vectors. So it's if there's a common factor in all three terms, you can just lose it. And I think I'm going to do that in this case. What else do we have? The constraining condition that x plus 2y minus z is equal to 5. All right, so let's go ahead and write this as a system of equations. There's going to be 3 equations from the 3 components of this vector expression, and then the 4th equation will be that x plus 2y minus z equals 5. Interestingly, wait, I just got to work through the analysis here. You know this, the zen of working with multiple equations in many variables? You have to have as many equations as there are variables, or you won't be able to find a solution. Right now we've got x, y, and z, but also lambda. And that's 4 variables. But there are 1, 2, 3 scalar equations out of that vector, and this is the 4th one. So that analysis is right, where we've got enough information to determine values for all the variables. In fact, we've got a little bit more information. They call this kind of thing overdetermined because, again, we don't really care about lambda. We can eliminate lambda. Okay. So ditching these 2's, the first one is going to be x equals lambda times 1, or x equals lambda. The second one is going to be y equals 2 lambda. And z is going to be equal to negative lambda. So far, so good. And then x plus 2y minus z equals 5. So that's our system. It's 4 equations and 4 unknowns. Will we be able to get anywhere with it? One thing I notice, I can just eliminate x from this. Replace x with lambda. I can replace y. You know what? I can eliminate everything except lambda by replacing these things with what they're equal to if I stick lambdas in. Wow, that's strange. Let me just try it. X is lambda, y is equal to 2 lambda, z is equal to minus. Let's look at this last equation if we just rewrite everything in terms of lambda. The x becomes a lambda. Twice y will be 4 lambdas. And then negative z is equal to lambda. And that should be 5. I just replaced x, y, and z with what they're equal to in terms of lambda. Well, that actually lets me figure out what lambda is. I never wanted to figure out what lambda is, darn it. But here we go. This is 6 lambda equals 5. So lambda is 5/6. And once I know what lambda is, that's weird. Right? That's not usually the way I approach these things. I usually eliminate lambda. But in this case, finding out what lambda is great because once I know what lambda is, I know what x is, I know what y is, and I know what z is. So that's generally what we care about. X is lambda, 5/6. Y is twice lambda, 10/6. Which I think we can sort of break it to 5/3. Yeah, and then z is the negative of lambda, negative 5/6. I think we're supposed to go back and just verify that this triple of values, x, y, and z, actually satisfy this constraining condition. But I believe we kind of have already done that in this algebra. If you want to check, 5/6 plus 10/3 minus 5/6, though that's 10/6 because of these two, minus. So, okay, I'm just going to say, use your calculator to check it. That'd be good. All right, last thing I want to do, mention something that's sort of outside of the course. But, if anybody's got an interest in the business world, this is an idea or a method that people talk about all the time in business. It's called linear programming. It's actually closely related to Lagrange multipliers. Because it's an optimization problem. The idea is to optimize a linear function subject to some constraining conditions that are themselves linear. And I'm not going to go through the whole generality of linear programming. I just want to give you an image of how this business plays out. Usually this is done in the business world to find the mixture of maybe items that you're selling, that you would, what's the ideal mixture of items that you're selling that'll maximize your profit. And so there's some conditions that are just really immediate from a setup like that. If I've got two products and I'm selling X of one and Y of the other, well, X and Y have to be positive. I can't sell a negative number of toasters, right? I can't sell a negative number of microwaves. So positivity, that means everything lies in the first quadrant, or that line, Y is greater than 0, applies. Everything above the x-axis, and because of this line, X is greater than 0, applies. But you'll also have these other constraints that come in that are linear. Things like, maybe the most my factory can produce is this many of the two of them. This would imply that maybe X can be made more rapidly or with fewer people involved than Y could, so if the slope was like that. So you may have a condition like that. You're in this sort of triangular region. If I make it just a tad more interesting, we could have another linear constraint, something like this, where we're on this side of that. Now, overall, what we've got is a four-sided region right now. It's in here, and there, above there, and to the right of there. So the region we're interested in, and this is known as the feasible region if you're doing linear programming, is like that. And then you have some objective function. That's the linear function. This is normally, if you were doing this for a manufacturer making two kinds of products, it would be profit. Now, from the Lagrange multiplier's perspective, this is pretty easy. Because what we want to do, I need a different color for this. And all I've got is black or red. There we go, got a green marker. So there's some function that's linear. What does the contour lines of a linear function look like? They are just horizontal lines, separated, evenly spaced across the whole region. Sorry. And where is the maximum of this? Well, it's in the direction of, it's going to lie somewhere where this bounding curve is tangent to the direction of that. That is, that guy has a gradient that way, right? And if we're, imagine traveling around that other thing as a driver on a road, we've got a vector that points out to out the right window of our car. And just as we're making that turn, that's where we would see that gradient vector pointing in the same direction as this guy. This leads to a piece of math, or a piece of, well, it's almost engineering at this level, but originally it was developed by a mathematician. It's called the simplex method, which is basically, if you have this region that's what's feasible, the maximum value always happens at one of the corners. It's possible that if these green lines were twisted just a little bit, that they would run parallel to one of the edges of the region. In that case, the maximum value happens anywhere along that edge connecting the things, but it also happens at the corner. So the simplex method is basically a way to intelligently search through the corners of a feasible region. This picture is two-dimensional, and so you might not be impressed by that, but the real optimization problems that people were interested in solving may be 50-dimensional, they may be 500-dimensional. There end up being dozens, if not hundreds, of constraining conditions that are all linear equations. But all of that stuff, it just comes down to search through where the corners are. And you can work your way through the corners of the thing by this simplex method until you arrive at the one where the function is maximized. It's kind of cool. It's been argued that the simplex method was what basically let the Allies win World War II. I think, that's a hard case to make. There's also cryptography, where like the Americans and the Brits both were good at breaking codes of their enemies, so they knew what the other people were about to do. And there was also, nuclear bombs. But, the war in Europe was over by the time that happened. One of the, in a work of fiction, I once heard the progress of World War II being the process of completely burying the Germans under manufactured goods. That the folks back in the US started making war materials and sending it across the ocean, and then people just brought that stuff into Germany and they couldn't outcompete us. Well, this is a type of mathematics that was used to optimize production of things, making tanks, making aircraft, stuff like that. So in that guise, this simplex method and linear programming did in fact make American manufacturing hugely more economical, more what's the right word? Efficient. And so perhaps you can make the case that if you view that war as having been just about the ability of America to outproduce the citizens of a relatively smaller country, Germany. Of course, they had Italy and Japan working too, but yeah, we beat them by making enough stuff that we could beat them. Anyway, the simplex method had a big role in that, and I guess that's where I'm going to end today. It's a method that you can think about in terms of Lagrange multiplier ideas, and if you're interested in sort of looking into the business world, you may enjoy looking into this. It's kind of amusing to me that this is a little bit of a side note in a Calc 3 class. This is the thing that really cuts the wheat from the chaff in most MBA programs. If you're going for an MBA, a Master's in Business Administration, some people can master the ideas of linear programming and the simplex method, and the other people can't. And that's the good CEOs are the ones who can use this tool effectively. Actually, in the end, the good CEOs don't have to do this themselves because they tell people to do it, but they need to know the ideas underlying it. Okay, so that's it for today. See you on Wednesday. We'll have a fun worksheet on this stuff. Ciao.